All right, everybody, this is Unit 5, Chemical Reactions and Balancing Equations. So a lot of you guys have had balancing equations before. If you have, you can probably skip down towards the bottom of the video. If you haven't, I encourage you to watch carefully. I'm going to walk you through some really simple ones, and then we're going to get into some challenging ones. There is a worksheet posted as well for homework that you can take a look at. So again, if you feel like you are good at this, you can, jump ahead and just do the worksheet. And we'll go from there, okay? So, just basic lingo. Everything to the left of an arrow on a chemical reaction, it's called a reactant, or sometimes a reagent, right? Same thing. Then we have an arrow. And then we end up with products. The arrow, it means yields or like goes to. It's not an equal sign, okay? So just be careful with that. It means goes to, turns into, yields, okay? So we have reactants on the left, products on the right, okay? Sometimes, and we'll talk a lot more about this in later units, you might see an arrow to the left as well, or both arrows, okay? Some reactions are reversible. Some reactions go entirely forward, some reactions go backwards, some reactions go a little bit of both. We don't need to worry about that entirely right now, but just don't be thrown off if you see arrows going in opposite directions. It just means it's a reversible process, okay? Another thing you might see, if there is anything listed above the arrow, that's a catalyst, okay? So if anything is written above the arrow, it's a catalyst. It's not a reactant or a product. And the reason is because it doesn't get consumed in the reaction. It doesn't get produced in the reaction. It is there in the beginning. It's there at the end. It remains unchanged. Its only job is to speed up the process, okay? Examples of catalysts are heat, some heavy metals like platinum, lead. Lead is a good example, okay? So you might see something written above an arrow, and that just means it's a catalyst, not part of the reaction at all. It's just there, okay? The other thing you might see are states of matter, right? So solid, liquid, gas, and the other option is AQ, aqueous, dissolved in water. In other words, it's a solution, not a pure substance, okay? So, let's give an example. Okay? Hydrogen gas plus oxygen gas gives us water. This is called the fuel cell reaction. This is incredibly energetic. Hydrogen-powered cars run on this. The space shuttles run on this. Like, insane amount of energy comes out of this reaction. Okay? And it is a result of hydrogen gas. So what we do is we'd write gas in parentheses after it. Gas. Okay? When those two things react, okay, we get water. Now, water is super stable, right? Water is normally a liquid. However, because this process produces so much energy, we actually end up with water as a vapor, as a gas, right? Because this actually happens at such an aggressive temperature, okay? We can also sometimes write energy as like a thing in the reaction, or heat, right? Again, we're going to talk a lot more about this later on, but that just gives you an idea. So, for example, when the space shuttle runs, we take hydrogen gas, we react with oxygen gas, and we produce water. And because water is so stable, all that energy has to go somewhere. And it is usually harnessed as heat or mechanical energy, right? To, for example, run the space shuttle, okay? So you might be asking yourself, well, that doesn't really make sense. We don't have enough stuff, right? We have 2 hydrogens, 2 oxygens, because that's how those things live in the world. But we get only 2 hydrogens and 1 oxygen. So we're short an oxygen. Something's not making sense, okay? But what we know to happen is that hydrogen gas, oxygen gas, react to form water. We know this. We have documented this. We have isolated the water from this, okay? So this is, in fact, what happens. Clearly, we have to account for the law of conservation of matter, right? All atoms have to remain intact. So if I have, for example, 2 oxygen atoms on the left, I have to end up with 2 oxygen atoms on the right. But I also have to honor the reaction, right? Like the thing that I know happens. And the best example I can give for this is like, you're baking some chocolate chip cookies, right? It sounds ridiculous, but think about it. If I say, I want you to bake a batch of chocolate chip cookies, right? So you go to your cupboard and you get the flour and the sugar and the chocolate chips and all that good stuff. You get everything out, right? You lay it all on the counter. And then you pull out the recipe and you figure it all out. Do you think that you have exactly in your cabinet the amount of sugar, flour, chocolate chips, vanilla, whatever it is? Do you think you have exactly those amounts in your cabinet? And the answer, I hope, is no, right? You're going to have leftover of some stuff. You're going to have not enough of some stuff, right? You're going to have to kind of figure out in your head, how much stuff do I have so that I can make the recipe, right? Because that is what you're following, the recipe. So a balanced equation is the recipe. It's not how much you have or how much you're going to have or whatever. It is the recipe. It is the reaction that's going to happen when these things mix, okay? Your job is to figure out how much stuff do you have, right? And then based on the recipe, how much stuff can you make, right? It doesn't matter that I have 18 pounds of sugar in my cabinet. If I only have 1 package of chocolate chips, well, I can only make 1 batch of cookies, right? And I'm just going to have a crap ton of sugar left over. It doesn't matter, okay? It's all about following the recipe, and that's what the balanced equation is, okay? So I have to account for all of these atoms. The best way to do this, draw a line down the arrow. List all the atoms present. Hydrogen, oxygen. Take inventory. I have 2. I have 2. On this side, 2. 1. Identify the problem. Fix the problem. Okay? I need more oxygen. Now, I cannot just put a 2 there. That changes the compound. That makes the compound H2O2, which is not water. That's hydrogen peroxide. That will kill you. Water will save you. Big difference, okay? Can't do that. Can't change the formula, okay? What you can do is change the quantity. So what I could say is, what if I make 2 waters in total, right? That would mean that I get 2 hydrogens, but I would also make, 2 oxygens, but I would also make 4 hydrogens. So I fix one problem, screw up another. That's okay. Go back. Okay? So now I'm going to go over to the left side. I need 4 hydrogens. What can I do? Well, I can't just change that. That's not allowed. Okay? What I can do is put a big 2 out in front. Put a big coefficient. And if I do that, things work out. Right? Now I have the proper amount of things. This is my recipe. I need 2 molecules of hydrogen to react with 1 molecule of oxygen in order to give me 2 molecules of water. That's the only way this works. Okay? But that is how this happens. That's the reaction we see with the fuel cell. Okay? And so we have to pay attention to that. So let's try another one. Methane, which is a gas, reacts with oxygen gas to give me CO2 and water as a gas. Okay? This reaction happens this way. I can't change the compounds. I have to add up the atoms and make sure everything works out. Best thing we can do, draw a line. Identify the atoms present. Add them up. Carbons, hydrogens, oxygens. I have 1, 4, 2. 1, 2, 3, right? Add up both compounds. I have 2 here, 1 here. So we have multiple problems here. Pick a problem you think you can fix it. I'm going to start with the hydrogens. I think I can fix the hydrogens by putting a 2 here. That changes that to 4, and that changes that to 4, right? 2 oxygens, 2 oxygens. Now everything works except oxygen. So go back to the left. Can I make this oxygen 4? I hope you're realizing yes by doing that. Okay? So that is the balanced equation. You're going to look for coefficients that you need to put there. If you need to, lay it out like this and go from there. Let's try one more, and then you guys can work on the worksheet yourself. Okay? Okay. Here is a acid-base reaction. Okay. We have the base calcium hydroxide, which is a ionic substance, but that dissolves in water. So we're going to write aqueous, aqueous, liquid, aqueous. Okay. Now we have to figure out quantities. Draw a line. Calcium, oxygen, hydrogen, chlorine. So we have 1 calcium, 2 oxygens. We have 2 hydrogens plus 1 here. We have 3. Chlorine is 1. Now go to this side. Calcium, 1. Oxygen, 1. Hydrogen, 2. And chlorine, 2. Lots of problems. Pick a problem that you think you can fix and fix it. Okay? So, let's take the chlorines. That looks like an easy one to fix. There's 2 chlorines on the right. I'm going to put a 2 here. See what that does. Right? And that makes 4 hydrogens. Okay? Now I need 4 hydrogens on the right. So I'm going to put a 2 here. 4. 2. And it looks like that is correct. Okay? So that is the balanced equation. And that's how you do it. Okay? Add everything up. Figure it out. Go back and forth and back and forth and back and forth until you can get the numbers to add up for you. Okay? And then go from there. There is a worksheet posted. Try a handful of them. See how you do. And we're going to practice next class. Okay? Again, some of you have had a lot of this and some of you have had none of this. So, do as much practice as you need to and bring your questions to class. Okay? All right, guys. We'll see you.